Good morning, everyone. My name is Rakesh. I'm working as a user support analyst at CSE. A bit of background about today's presentation. It's about introduction to SLURMs, some of the basic concepts that are there in SLURM. A lot of the material that I have taken here is from one of the workshop that we attended a few months ago. It's an introductory workshop given by someone from SkidMD, and this is just to share what we learned from that particular workshop to a wider audience, but a much condensed version of it. To begin with, this will be the outline of my presentation. First, I'll go over a quick overview or an introduction to what SLURM is, and most of you, as analysts, working with Alliance, might be aware of these things, but just to give you an introduction to what SLURM is, followed by job submission scripts, how we submit jobs, then some of the useful utilities that we can use using SLURM. These are SLURM user commands. Then I will look into SLURM configuration files, followed by job scheduling. How are jobs scheduled using the SLURM schedule? First, to begin with the introduction of SLURM, this will give a quick overview of the architecture, the components that we have, what are the daemons that are available in SLURM, and how does the job launch sequence works. To give a quick overview, this is the frontend cluster that we have. We have 3 login nodes and compute nodes, and scheduling, and one a storage unit called GPFS. And we use SLURM to schedule jobs by typically what happens is users log into the login nodes, and they submit jobs to the compute node. Essentially, SLURM is a scheduler, which this stands for Simple Linux Utility for Resource Management. I don't think it's no longer a simple code. It has close to 500,000 lines of C code written in it, and it's completely open source. And more than half of HPC clusters in top 10 uses SLURM as their resource manager. This is developed in Lawrence Livermore back in 2022, and it's supported by SkidMD. What does SLURM do as a resource manager? It allocates resources with certain time limits. When a user submits a job, so a certain amount of resources in terms of CPUs or GPUs or memory is allocated to that user for a certain time period, and it takes care of enforcing these resource limits for each of the processes that runs under that user during that particular time frame. The job priority is based on the defined scheduling policy for that cluster. Typically, we use something called multi-factor plugin, and I'll come to that in a little bit, but it depends on the scheduling policy that is used for each of these clusters. And SLURM also maintains the job queues when typically clusters are oversubscribed, so the SLURM maintains the job queues. And it also provides a framework to enable inter-process communication on the clusters. Typically, we have parallel jobs that are each process is communicating with each other to run the simulations, and SLURM enables these communications to happen between the processes that are running on each of the nodes. To give a quick overview of SLURM architecture and design, the SLURM management nodes contains mainly a SLURM control daemon, SLURM CTLD, and a SLURM database daemon. And we also have an SQL database. It could be either MariaDB or MySQL, which stores all the accounting and configuration records within the database. And we can use user commands. When I say user commands, these are SLURM utilities both for the end user as well as administrators to communicate with the SLURM. Either this is not a very exhaustive list, but like most of the commands communicate directly to SLURM control daemon to get necessary information or to launch their jobs or to submit their jobs. And we have two utilities called S-Account Manager and S-Account, which communicates with the SLURM database daemon to retrieve accounting information from the database. So there is no direct interface to a SQL database that are installed on it, but most of the communication happens through SLURM daemons through retrieve information about current running jobs or accounting information through SLURM DVD. So SLURM is a very high fault tolerant system with high availability. For that design, like essentially we have SLURM control daemon and a backup control daemon. So whenever a SLURM control daemon, the primary control daemon goes out of communication, the backup daemon kicks in and takes care of job submissions and running the jobs and keeping the orchestration alive. Typically, what they recommend is like to have SLURM primary control daemon on one node and backup control daemon on the second node, like for the failover. And on the second node, like we should also have the SLURM database daemon. The reason for that is if, for suppose, the second node goes incommunicado, like the SLURM can still submit jobs. Like we can still submit jobs and run the simulations without failure. The reason for that is SLURM control daemon on the SLURM control daemon node, it maintains a cache of the current state until a certain point, like when the cache is not filled, it can still take jobs and run jobs as they come in. And all the jobs are launched through SLURM daemons, and the communications are established through SLURM daemons, which are more lightweight and installed on compute nodes, essentially. SLURM doesn't work on its own. Like there are a couple of infrastructure or libraries that we need for SLURM to run. One of the thing is munch keys. Like for these are necessary to provide authentication to enable communication between the compute nodes, because we have different compute nodes, and if they need to communicate with each other, we need some sort of authentication, and munch is one of the authentication provider. And second thing is network time protocol servers. This is to maintain a uniform time across the cluster. And since all the communications are time sensitive, we need some mechanism to maintain the time across the clusters, and NTP is used for that. And then we have SQL databases. It could be either MySQL or MariaDB to store the accounting information and configurations. And then we have HW logs, like these are portable libraries to retrieve information about the compute resources. This includes the sockets, number of cores that are available, and nodes, and so on and so forth, and memory, and a couple of other things. That's a quick introduction of like how SLURM is set up, or how they recommend SLURM to be set up. Coming to the control daemons, like central daemons, like we have SLURM control D, which is the central controller. This is the control daemon that monitors the state of the compute nodes, manages the job queues, and allocates the compute resources as the resources become available to the jobs. SLURM DVD is mostly used to collect accounting information from a database. When you call S-Account or S-Manager, it goes through SLURM DVD, like I mentioned, like to retrieve information from the database to the end user. And it also maintains accounting information, how much usage a user made or a group made during a particular time frame. The control permissions in the sense like which user can access which nodes are partitions, and it keeps track of all the job steps, and so on and so forth. Like when SLURM database daemon goes down or it goes responsive, like I mentioned, the jobs can still be submitted. In this scenario, just control daemon references the job info from its own cache. But if the SLURM daemon, DVD daemon goes away, like any changes to the job or access controls in terms of QoS and things like that, they can't be made because there is nothing available to write that information to. So that's one thing. One thing that's noted in the manual is both control daemon and DBD daemon shouldn't be launched as a root user, but typically you should have a non-root user. We can call them SLURM, like to launch these processes essentially. Coming to the daemons that we have on the compute nodes, there is SLURM daemon, which is a much lightweight application compared to SLURM control daemon and SLURM DBD daemon. Like essentially, one control daemon runs per node, and it's usually a lightweight application, and this takes care of launching the job. And the actual job steps are actually managed through SLURM step D. And if you have a large parallel job, SLURM daemon supports hierarchical communication in the sense that SLURM daemon can communicate with other compute nodes just to in a fan-out pattern to communicate with other SLURM Ds on other compute nodes instead of going to the central daemon that we have on the management node. And on compute nodes, SLURM step D does a lot of heavy lifting in terms of this is also a lightweight application, but like it launches if you launch a job by srun, SLURM step D essentially shepherds the job steps. It launches the user application, and it also manages the communication process between the applications to srun. This particular figure, I have taken it from the SLURM training manual from SCEDMD. Like what essentially, when we submit a job, essentially we are submitting it using sbatch, slock, or srun. These are the three commands that are used to launch a job to the cluster. When we do this, what typically happens is if this is srun is not typically used to launch a request job allocations, but like if you use srun or sbatch, what happens is srun sends a job allocation request to SLURM control D, and then based on the availability, SLURM control D allocates the allocation, provided it has found some compute resources that can run for the job. And this can be taken care by sbatch or slock as well. And in the second phase, srun sends step create request to SLURM control daemon, and SLURM control daemon responds by giving the credentials that are required to open the sockets for the srun. And srun forwards these credentials to SLURM control D. And essentially, this SLURM daemon communicates with other SLURM daemons in the compute node, or forks or like launches step D to manage the tasks. And in steps 7 and 8, it essentially SLURM D communicates, step Ds communicate with each other through srun. And once the job is completed, like the resources are given up, like step Ds send a termination report. And once these are received by the srun, like this, it's communicated to SLURM control D. So, and SLURM control D verifies, runs the epilogue scripts and things like that, and like terminates all the processes and does all the cleanup work essentially. That's a quick overview of how the jobs are launched on when we submit SBatch, SLOC, my job script, and so on and so forth. The next session will be on job submissions. Like I think everyone here is more or less familiar with this. So I'll skim through these topics, but these are the topics I'll be covering. Like one is how to submit jobs to the compute node, an example of a job submission script, what SBatch directives we have, and array jobs, which are typically used if you want to run parametric analysis or simulations with conducting with various input parameters, essentially. This is ideal for that. I'll come to it like about GNU parallel when I get there. There are three ways of submitting of running a jobs on or simulations on compute node. One can be through SBatch, SLOC, and SRun. So SBatch is the most common way to launch a job non-interactively, and SLOC is typically used to get an interactive shell to submit job to run smaller jobs for a limited period of time, just to make sure either you're conducting some diagnostics on your simulation or you're just verifying if your code works or debugging your code. That's when SLOC sessions are more useful, but the actual jobs are goes through SBatch for the most part, and I'm sure like everyone is already aware of it. One thing that I wanted to mention here is like there are in SBatch, like we define the resource request that we want using SBatch directives. There are three ways of doing it. Essentially, we can declare it as an environment variable. So that sets the global time limits for that user. Let's say if someone sets it in their bash RC, essentially like those are set as the global time limits for all the jobs that they submit. This can be overridden by typically everyone does the source compute request on by declaring the SBatch directives within the submission scripts as well. But sometimes we don't want, let's say I'm running a simulation for 1 day, but I don't want to run it for 1 day when I'm testing it. So I just quickly wanted to run it for 30 minutes or like 10 minutes or something like that. We can also pass the arguments through command line. This becomes this becomes really useful for me when I'm submitting when I'm testing someone else's job, because I don't want to run for the whole period of time, but like, and at the same time I don't want to change their job script. Like what I can do is I can just pass it as command line arguments, and this will override whatever directives that we have set in the job submission scripts. That's one useful tool. And if we come to the SBatch directives, these are the SBatch directives that we have. In my opinion, like at least 4 of these have to be defined, like although it's not a requirement in the sense like number of nodes that you want, number of cores that you want, either in terms of end tasks, if you are running an MPI program, or if you are running a multi-threaded program like using OpenMP or something like that, like then you have to define CPUs per task, the time limit, and memory used per that job. In my opinion, the rest of this can be optional, but the job script should typically have at least 4 or 5 of these. If you are using GPUs, obviously we need to include CRES equals GPU and number of GPUs that you want. So if we look at the job submission script, what we have is SBatch shebang to specify the shell, and then we have SBatch directives to define what are the compute resources that we are asking for, and followed by the script that you actually want to run. This could include a couple of modules that you want to load to run your simulation, followed by the actual command to run your simulations. This is just an example of how it would look like. And then we do SBatch submit .sh. And once we do that, once resources become available, the jobs will be launched using this particular sequence, essentially. I summarized a couple of SBATch directives that might be important on a day-to-day basis. Like this is not a very exhaustive list, but it could be a couple of things that are useful. We can define, for example, like if we want to ask for multiple cores, like we can define it in terms of total number of cores that we want in terms of n tasks, or we can ask it per node, or per core, or per socket, or per GPU. Same thing with CPUs. You can ask it for per task or per GPUs. These are the time limits. And sometimes like one more thing that I noticed is like you can also specify the maximum time limit and also the minimum time limit to schedule your jobs. This is especially useful if people are checkpointing, I guess, like and they don't need a specific time, but like if they can get resources like that, they can use that. There was a question to know if recordings are presented. Yes, there was a question. Yes, we will share the recordings or the links to the recordings and the presentation file. Yes. It might take some time to upload it, but like it's a smaller group, so we can email out. I can email out the presentation as well. And then these are some of the directives like that might be useful. These are some things I found that are most commonly used. Same thing with these are some of the things that you can use in addition. Like so let's say if you are running a parametric analysis, like we have a dash array to specify an array job. What it essentially does is, but through a single job script, like you can submit multiple jobs using array jobs. That's what it is. And also you can specify the amount of temporary directory that you want for your allocation. This is useful when people are doing high I/O to the hard drive. Like we typically don't recommend that. If there is a workflow that needs to do that, it's better to do it on the local storage rather than the global storage that we have, GPFS or cluster systems. So that's you can request for that. And like people can submit to users can submit to a particular partition QoS, and if there is a troubled node, like we can say that exclude that using the exclude directive. And also what happens is there is a default behavior in SLURM on what environment variables are exported from the current working environment on the login node to the compute nodes. We can specify either to import everything or not import any, not to or give it as a blank slate, like just to purge all the environment variables that we have on the compute nodes, on the login nodes essentially. And there is one flag called dependencies. This is really useful if you are running array jobs, or if you have jobs. If you're running two jobs and the second job depends on the first job, like first you're running a simulation, in the second job, let's say you're running some analysis on the results that you got from the first simulation. We can use -d flag to essentially specify how the second job can run depending on how on the completion of the first job. Oh, sorry. I misread. The first directive is exclusive, which means that no one else can run on the system. Exclude means like to exclude a list of nodes that are excluded in the system. And we can also specify the node list of where the jobs can run, and so on. Coming to the array jobs, this is really useful if we want to submit multi-user, multi-threaded or multi-core job, and you have a lot of job parametric analysis to do with different input parameters. A job array is an ideal way to do it. This is, like I mentioned in the previous slide, we can define this using -- array equals the size of the your job array. In the first scenario, I'm specifying 1 to 100. So 1 to 1,000. So 1,000 jobs can be launched with a single job script. And each of the job gets a task ID, a unique task ID, and that can be identified in the job script using SLURM array task ID or percentage a variable. There are few other ways, like suppose you don't want to launch all the 1,000 jobs or 200 jobs at one time. There is a way to throttle or limit the number of jobs that can run simultaneously. If we use the %50 symbol, which it says that run the jobs 50 at a time. So if one of the job completes, then the second, the 51 job essentially begins to run. Or we can say discrete values for the task ID. In this case, it ranges from 1, 2, 6, and 7. Those values are essentially assigned to SLURM array task ID, and those can be used to run the parametric analysis. And lastly, we can jump the increments by a particular value. In this case, it jumps by 20 for each of that particular value that we have. Just a quick heads up, like it's a small group, so if anyone has a question, feel free to unmute and you can just ask the question as well. That's the end of the job submission. I'm assuming most people are aware of this, like, but if you have any question, I'll pause for a minute or two just to give some time, like if anyone has any questions before I move on to the next segment.
Hello, can you hear me?
Yeah. Yes. Yeah.
Yeah, I'm just curious. So, will you be able to like do a demo later, like by the end, like in the last part of the presentation, like from scratch, like a user creating a job or maybe a script and then running that script in the SLURM, then maybe
Yeah.
yeah.
Yeah, I think I have some user scripts that I used for one of the HPC course. Like I can do a quick demo of that, like right now. I think.
But if we still have like other topics to cover, then
Yeah. So yeah,
we
that's
can do it by the end of the like in the last part.
yes, yeah. That's a good point. Like I can do that, and also like one thing that one note that I want to mention in array is like. A lot of the times, like people submit array jobs even if they're running a serial job. Like there is some other command called GNU parallel, which essentially launches multiple serial jobs using a single array job. Like one of the advantages of that is like it doesn't create multiple files based on how it's set up. That's one thing to consider. I'll also cover that in the demo session. So thanks for asking. Coming to the next part of the presentation, like I will go over quick some SLURM utilities that we can use when we want to retrieve information, when someone opens a ticket, or like if we need some stats about how the jobs are running and things like that. There are or how to submit jobs. There are user commands. User commands are essentially our interface from the shell that we are using to the SLURM control daemon or database, essentially to SLURM. That's your main mode of communication. So like I will quickly go over the commonly used ones. Again, this is not a very exhaustive list, something that we can use. So we have sbatch, slock, and srun. These are used while running the job or launching the job. So sbatch, like I mentioned in the previous session, is to submit a job non-interactively, and slock is for an interactive session. So you can make the source request with a particular request particular compute resources, and that will give you the resource for a limited time frame. Usually, our interactive partitions have lower time limits. I think on most alliance clusters, if I'm not wrong, it's 3 hours. And for S batch, it can range up to 14 days, if I'm not wrong, or 7 days. Then we have SQ and SCancel. These are essentially to monitor what jobs are in the queue. Like SQ essentially gives all the jobs that are currently running or pending. And SCancel is if I launched a job and I saw something is not working, if I want to cancel it, or if I saw some user job using up a lot of resources that it's not supposed to, like typically this happens with IOPS, like a lot of input output operations are being done by that simulation, and we want to cancel it for some reason. SCancel is the command to use. And then for monitoring and reporting, we have SStat, SReport, and SF. This is essentially, SF is essentially to report on efficiency from one of the jobs. I think there's one more. Yeah, so S-Prio, which stands for SLURM priority, gives you the components of the scheduling policy. This is this command is only to retrieve information. Like when a job is submitted to the scheduler, essentially every job is given a particular priority value, and based on that, these jobs are essentially ranked to say which job is going to run at what time, based on the availability of the compute resources. S-Prio like gives a glimpse of how those priorities are set up and what those priorities are, priority numbers are for the whole list of jobs that are in the queue. And S-Share is to retrieve information about the accounting details in terms of usage, as well as shares, how many shares that a particular account has as a user has, or the amount of usage that a particular user has used till date. S-Info gives you information about nodes and partition for the most part. Like that's what at least I use it for. And S-Control is one of the command. It's kind of a Swiss knife of SLURM utilities. It's one of those commands that communicates with the SLURM control daemon and retrieves a lot of information about configuration, the state the current compute nodes are in, and so on and so forth. And then we have S-Account and S-Account Manager. These are two daemons that communicate directly with the SLURM DVD, which essentially retrieves information about accounting data and to modify any accounting information. In the top scenario, almost these commands are essentially for the end user, SF, S-Prio, S-Share, and S-Info. S-Control, based on whether you want to display the information or modify the configurations, it caters to different user groups. Like it can, if you're displaying some information through S-Control Show, which I'll be showing in a little bit, it's more for the end user. But if you're using S-Control Modify or Add or something like that, it's more for the system administrators. It needs admin privileges to make changes for obvious reasons. Same thing with S-Account. S-Account is meant more for the end user, like the actual users that are running the simulations. And S-Account Manager is for the admins to make any modifications when required to the accounting information. I will quickly go over 3 of these user commands. As analysts, we might be more interested in this because like to some extent, we have used SPatch, SLOC, and SRun. SControl, SAccount, and SManager is somewhat to retrieve some information about the jobs that are running on the cluster. And also it becomes more important while we are troubleshooting. Same thing with SShare and SF as well. But I will be more focusing on these three commands due to the time frame we have. To begin with, SControl is used to modify the SLURM configuration, to view or modify the SLURM configuration related to the jobs, partitions, and node configurations. Some of the commands, like especially SControl update, create, or delete, requires admin privileges to make the changes. SControl directly communicates with control daemon to view or modify the current configuration that we set up using the configuration files that we have in SLURM folder. The changes that we made only are valid for the duration of the time that the SControl daemon is running. If it reboots, it goes back to the configurations that we have in our configuration files. There are a few ways to update it. We can use swrite to save the configuration, or we can directly go to SLURM config files and make the updates directly. So coming to SControl, right? Like there is one command called, which I came across while reading through this, is there is SControl write batch script, which essentially writes the batch script of the job to a particular location that you wanted to be returned to. And then we have sconfig, which essentially saves a configuration file with this output format, like slurm config dot the timestamp, and that will save the state of the current configuration to a particular configuration file. I believe it's typically an XC slurm on the slurm controller nodes. And also this list is not very exhaustive. So what I have given is, and I will be sharing the slides with everyone. So like this gives a quick overview of all the documentation that I have available. I'll quickly open the link. So the options I have given for SControl are not very exhaustive. It's a long list of commands that we have, and at the end of each command page, like I have given a documentation, a link to a documentation to the actual SCADMD. And one thing that I noted with the SLURM documentation is that indices for the like the manual page is not at the top, but at the bottom. It might be more handy to navigate if you are looking for, let's say, if you want to update a particular thing, configuration, or if you want to show a particular configuration, like you can jump to that about a particular running job. You can jump to that to find the respective options that we have to run the simulation. That's one thing. Moving forward, like so the command line argument for SControl goes something like this. We have SControl and the command that we want to do, a command that we want to run. This could be show, update, create, delete, or write. There are more options than this, but the typical ones are these. And then you have to specify what needs to be done, like and also the entities that need to be changed, and finally the output format in which it needs to be printed out. That's the typical command line argument for SControl. So if I want to run SUpdate, I have a couple of options available. I can update the accounting information or the job ID, user ID, number of CPUs available for a particular job. These are all for the jobs. I can increase the time limits or decrease the time limits. End user, I believe, can decrease the time limits, but not increase the time limits. If we want to increase the time limits, someone with admin privileges have to do it. But on Alliance, we have two scripts that gives us admin privileges for a couple of things. One, to change the priority of the job, and second thing is to increase the time limits if we have to. They are CCSL prio and CCSL wall, and I'll come to that in a little bit. And if we want to change the node partition that it runs on, that can be done as well once the job is submitted. These are some of the things that S-Control can do. Like I said, it's one of the Swiss knife to control how the jobs are run, to change the configurations essentially. Then we have, we can upload the nodes as well. Some of these can include, let's say, if we added a GPU to the node or something like that, we can update the address or the node name or the state. Like sometimes there is a misbehaving node, and if you want to put it down, we can use S-Control to drain a node or to resume a node once it gets back. And also, like when SLURM is assigning the priority on which node to run, there is a particular specification in the config files called wait, which essentially sees SLURM makes use of this particular variable to assign on which node in a particular partition should a particular job start first. Like if let's say there is nothing else and there is only one node that's one job that's coming in, and in that case, SLURM uses weights assigned to each of these nodes to essentially say where the jobs will run first. This we can typically use when let's say we have a large node and a small node, and there is a small job coming in. Probably we want to assign the smaller nodes, small memory nodes, a smaller weight than the bigger ones, because we want to start simulations. We want to make use of that smaller node first before we go on to the larger nodes. That's one use case for this. And again, we have show command to essentially display the information. These are essentially available to all the users. If I do S-Control show alloc and my job ID equals something, it can essentially, when the job starts running, once the job starts running, when I run this command, it can show that what all the nodes that is allocated to. That's useful function if you want to quickly check, like and then we can also see job states, or we can request how much tasks are requested for this job, and also when the job was submitted and what nodes it's running, and so on and so forth. For nodes, it can also show the state of the nodes as well. Some of these specifications include amount of memory that's allocated for a particular node, the state, amount of free memory that's available, real memory or user specification list, and number of CPUs that you have in that particular node, and so on and so forth. Again, like this is not a very exhaustive list. I listed a few of the things that might be useful, but an exhaustive list can be found on the S-Control documentation. To quickly go over a couple of examples, I'll probably do it on our frontend cluster. So if I want to find a specs for a particular node, I can do S-Control show node CAC 034. And that will essentially show the information about the interactive node. So I have, what's the CPU? This is one of the interactive node that we have. Like we have total 24 CPUs on it. What's the amount of memory on it? Like it looks like this node is pretty much ideal right now. So the real memory, allocated memory, and some information that we can make use of when we are trying to see the state of that particular node. I won't run this command, but like just to show, I'll probably copy it without sudo because that won't run. Control update. Let's say if we are facing an issue with one of the nodes and it needs to be drained, we can do that. I don't think this node exists, so and I can say that state equals drain, and that will drain the that will put the node out of this in a drain state, essentially making it unavailable for the scheduler, and we can use update command to do that. And if we want to know some information about the jobs that are running, we can run SQ. If I specify the username, that will give the amount of jobs that are currently running under this particular user. Because I don't have any jobs, it simply gives a blank, just the header files. If I want to see all the jobs that are running, I can just simply type in SQ. And those are all the jobs that are currently running on the system. If I want to know some information about a particular job, I can do that as well. Copy that. Let's control show job ID. So it gives it a lot of information, and I feel like this can be useful when we get some tickets on troubleshooting it. Most of the time, in my experience, we don't know the exact script that they use for a job or something like that. And this can be a really useful tool because it gives a lot of information about the job itself, in the sense, does that start? So it gives you information of who submitted it, which group it belongs to, which partition it is running on, and also which nodes it's running on. That's some useful information. The ask for the job in terms of dress, like is given here, and also like the commands that are used to submit the job, and their working directories where the standard error and standard outputs are going. So we can actually essentially go in and look at those files, and like it's easier to troubleshoot it. This information can be really useful when we are troubleshooting that, a particular ticket that we receive. I'll check what else we have. And we can, once a job is submitted, like if we need to update it, we seldom do this. In my experience, I have never done this, but there is an option to change the resource request as well. And let's say we have a teaching workshop coming up and we want to set reservations, we can do that using some control as well to create reservations for a particular period of time. In this case, I'm creating a reservation called teaching, and it starts at a particular date in the past, and it runs for 7 days. And everyone in the teaching account will be able to use this reservation, and it's set on standard partition. And again, if you want to delete it, you can just run this command to delete that particular reservation. Like I mentioned, in Alliance internal wiki, if you go to frequently asked questions, we have 2 commands that are available to us, some documentation on that. It is ccslprio and ccslwall. A lot of scontrol update commands need sudo privileges to make any changes. Essentially, not every analyst has sudo privileges based for the system that they're supporting. So we can use SSL prio, which is essentially, it'll bump up the priority of the job that to the top so that the job can start first. Like if there is a specific request and the analyst feels it's a legitimate request, we can use this command to put it to the top. Same thing with ccslwall as well. Like if a user is running for 2 days and the simulation is not completing, and like they need just a half a day of time, like just to increase it. The user can't essentially increase the time. Even we can't increase the time because it needs pseudo privileges. So we have a script called CCSL wall to increase the wall time. The exact documentation and how to use the command is actually in our frequently used pages for our internal wiki. Since it's an internal wiki, I just don't want to show it in the webinar. Same thing for account manager. Account manager is one of the tools to know more about the accounting information. Like I said, like it directly interfaces with the SLURM database daemon to retrieve information about the database. S account is meant for the end user, whereas X account managers is meant for admins. There are a couple of options that we can get from S account. Again, I put the documentation to the SCED-MD page at the bottom. You can get retrieve accounting information, batch scripts if they are running at the moment, if they are saved, essentially. Users, like if you want to retrieve information about particular user, we can use -u and -j for jobs. If you want to retrieve information about jobs that started in a particular time frame, let's say a particular start date and end date, we can this is the flags to use. And then again, if you want to know the state of the jobs, that can be used in here. So we can use a combination of these options. Like this is not just one option. In this case, for example, I want to know all the jobs that I ran since September 2022, like that's 1 year ago. So I can specify that S account, my username, Rakesh, followed by the start date of that particular thing, and that will retrieve information about all the jobs that started in the past during that particular time frame, from a particular start date to present. Like I can also specify the end time. Like if I want to look at the jobs that I ran during September, I can say 2022 0901 to 2022 0931 or 30. I can't remember, but that will essentially give you all the jobs during that period. Same thing. S account manager is essentially to modify or show accounting details. If you are displaying information, we don't need pseudo privileges if it's for that particular user. But if any modifications need pseudo privileges, I didn't show it specifically. But let's say I want to add a user to the teaching group. Like let's say I created a user accounts and teaching groups, and we created some student accounts, and I need to add to that teaching group because that's where I set my reservation for. We can use this command essentially to do that, and we can show some information about a particular user. Let's try that particular command right now. If I need this for that, so there PC operating. So that essentially gives all my user information in the sense of which groups I'm part of, the privilege, like the QoS. I have a normal QoS and a privileged QoS, and which groups I'm part of. Like this is the group, like cons HPC test and a default account, and these are some accounting information that could be useful. And I can also show associations for a particular group. In this case, let's see if it's a con or a def group. I think it's a con group. So that essentially gives the users that are under this particular account, essentially. So that's a quick overview of some of the utilities that we can use for running to retrieve some information. So if you look at the S account manager command, this actually is going and querying the SQL database. So that's where we see commands like where user equals HPCG, which are similar to what we find while we are querying, not exactly the same, but like when we are asking the database essentially. And also, if I want to modify an account and add it to a particular QoS or partition, I can do that using modify command as well. I'll pause for a bit before I move on to the next slide. If anyone has a question, they can either post it to the webinar or unmute and ask as well. Again, this is a small group.
Rakesh, I just have a quick clarification. So when you run S control, like show job ID, and it just gives the path of the submitted job.
Mm-hmm.
So if a user makes any changes to that submission script, like then there's no way we can track that, right? Like so by the time they submit a ticket to us, and then like
no, I think there's no way to show that. There is one more command called scontrol write batch equals. If you go to, I mean, any changes that's in this case, like it just showing the actual path. So
yes,
that's the path. Right. So if anything that's changed,
yes,
that can be stored. I'm not clear on that, but there is one more command called scontrol write. I never used it actually.
Mm-hmm.
Batch job ID equals something.
Okay.
And that might print out that might store the actual job ID. I still have to test it out. That's something we can look into.
Okay. Yeah. But because like the portal on Narwhal and like, a few other clusters that we have, like, that has like a tab that says like, submitted job. So, that exactly has the information on like, what the user submitted, at that particular time frame. So I just wanted.
Okay, like probably they're passing it from this batch script. I don't know.
Yeah, I guess so. Like, I think the minute it gets probably submitted, then you can actually check that on the portal. So
yeah. And batch script is all this information is only available for the current running jobs and some jobs that I've finished, but are still in the cache. But if you have a job that's been there like after a day or so, I don't think we'll be able to retrieve that information. It depends on your cache space and things like that, but that's
okay. Yeah, thanks.
Yeah. Okay. Again. Someone was, I think we have good amount of time. So like what I'll do is, I think Francis was asking about the batch scripts and things like that. So I'll just quickly go over that as well. There was a question about how to submit jobs, an example of that. So I have 3 jobs that are specified over here. One is a serial job, one that requires OpenMP, and MPI job. in this case, it's a very simple program that does some numerical approximations to calculate the value of pi. If you look at the job, it's a C code and it's pretty simple actually. So I set the value like number of, it's basically an integration of a function and a summation of a particular set of values integrating in a particular range. So this loops for 10 billion integers, and it calculates the area under that curve for each of these instances and sums it up, and roughly, and mathematically that's equivalent to pi, but when you're calculating numerically, that's roughly equivalent to the value of pi. That's exactly what this does. So if you want to run this job, like this is a serial job, like meaning it can only use one core. So I have a simple make file. Let me load the module just to be sure. Oh, sorry. Jesus. So I loaded the modules that I want to compile this via C program. Essentially, I need a GCC. So I did that, and if I look at the make file, it just compiles that and creates an executable. So I run make, and it created a file called this. Because it's a simple job, I'll run it on the login node, but it's heavily frowned upon if it takes any much more. Oh no, this has 10 billion elements. No, I won't do that. So if I want to run this job on the compute nodes, this is my job submission script. So remove this. Okay, the first three directives are essentially defining what are the resources that I want. It starts with the shebang specification is saying that it's a bash script that I'm running, and followed by S-batch directives, which essentially says what are the compute resources that I want. In this case, I need one node because it's a serial code. I need n tasks equals 1. And also by default, CPUs per task will be equal to 1. So I didn't specify that. And I want to run it for 10 minutes. And for each CPU, I'm just asking for 1. I need 1 gigs of memory. And I'm just timing it to give a sense of how much time it would take to submit this job, to run this job in real time, not the actual computational time. So I think I need to add a few more. Oh, I'll demonstrate this particular thing. There are a few more directives that I need to specify because this was meant for something else. I'm not part of the teaching account anymore. So if I run, let me see if I can run it with the teaching account. I say S-batch. This is the next two directives I'm specifying is not a requirement on Alliance cluster, like the partitions and QoSs and everything are taken care by that. Like our system is set up slightly differently, so I have to specify the partition that I want to submit to, at least if I want to run it a bit faster. And to submit the job, all I can do is sub dispatch job.sh, and that submits a job, and I can see the job in the job queue. Not the whole thing. If I type SQ, which is a shorthand for SQ is a name, and that submits a job. That's it. Yeah, Francis, you can unmute yourself and ask it.
Yeah, so it's understandable now, but I remember the job.sh. I'm just wondering, so if you create, if that file is in the system, right? Who is creating that bash script? Is it the end user, or is it
Yes.
the organization who is like hosting the SLURM?
It's the end user. Like we do provide some trainings on how to create these files, like at least Alliance does. And the end user is supposed to create this, because if you see the program, like a bunch of directives over here, there is no way for us to know like what the requirements are. These are specifications that the user has to specify. So based on these specifications, we have something called a job submit.lua. If I have time, like I'll get there, which kind of channels these two different partitions. They don't need to specify the partitions like I did here. But these are the 4 things that they have to specify. Apart from this, like I've shown in one of the slides a long list of things that we can still define. Typically, what I see is usually users define the mail type or the mail, saying that when they want, they just want a notification saying that like I have my job has started or finished and things like that. And also specifying a particular job name. Like by default, if you look at the completed job, if I do ls again, all the standard output is channeled to this particular file over here. And same thing with standard error. You see a dot error extension if there is any standard error. And if I do cat, because I was printing it to the screen, the output will be printed to the screen. Like value of pi is 3.14, and how much time it took in real time, as well as actual computational time, and so on and so forth. Because that's how I have written the file. But the whole thing, job submission script, is, in my opinion, end users' responsibility. We can definitely help them in getting the values right. Like
so I'm meaning to say, like a researcher should be like technically inclined before being involved with, creating scripts or something.
Yes, they need some some background in Linux, how to navigate it, because otherwise they won't be able to do it. Like be able to write the scripts. Usually what I find is, in most cases, like SBatch script is not that complex. It's simply the directives that they want to run, the modules that they want to load. And lastly, I forgot to put in the module load commands over here. And lastly, command line, the commands that they use to run it on the command line. So let's say if they're running Abacus or something like that, we have a wiki pages for that, specifying how to define that. But that's also becomes users' responsibility. But we can definitely help them. That's what we typically do in the ticketing system. But the script is their responsibility, and it's not too complex. It's simply a bunch of commands that they run in, like, to run the script, and like dispatch directives.
Yeah. I'm just trying to understand the whole process, like from scratch, right? So that's pretty understandable. One more thing. So you have the slurm dot 6382589.out. So once this file is created, does this mean that the job is already completed?
No.
Oh no. Okay.
So all the standard output is streamed through this. I don't know how often it's written, or like it's continuously written. I think it's continuously written. So yeah, this doesn't mean like job completed, but it does mean that the job has started.
Oh, okay. Got it.
Yeah, if you're running a parallel program using multiple processes, the job script will look similar, but a few things will change. Like I'll show that here. Why didn't I specify? So I didn't specify it here. I think I was making some changes. Yeah. I was playing around with the script, so this is not final. So essentially, I can define n task equals 4. I'm running in one node, and n task equals 4, which essentially I'm asking for 4 tasks or 4 processors to run my code on. And MPI run is a particular program that takes these number of processes and runs my simulation. So there are some environment variables that SLURM sets in, and you're using this sets to 4 when I ask for that, when it's scheduled, and my program essentially runs with 4 processors.
Okay.
Yeah. That's a quick overview of how to submit jobs, essentially. Okay, in the next few slides, I will be talking about SLURM configuration, how configurations are set up. And after that, I'll be talking about job scheduling, how jobs are scheduled. Once a job comes in, how it goes to the scheduler and how it gets scheduled on one of the compute nodes based on partitions. So in SLURM configurations, I'll be discussing about 3 configuration files, which is slurm.conf, grest.conf, and topology.conf. And then some information about partitions, which are essentially logical units into which the whole compute cluster is divided into. A set of nodes are combined together into logical units, and these logical units can have overlapping nodes. Essentially, that's what partitions are. And job submit.lua is used on Alliance cluster to redirect like the jobs that come in into a certain partition. These are the 3 things that I'll be discussing in this particular session. To begin with, we have mainly 4 important files that almost sets the configuration on SLURM. One is slurm.conf, like this is where all the node resources and partitions are defined. Then we have grest.conf, which stands for generic resources. This includes GPUs. There is, in the original, if we look at the slurm.conf, there is no way to specify the GPU resources that we have. So we use something called grest.conf to define a generic resource. Under that, like we can define GPU that are available. And topology.conf is more about how the network is laid out. And it essentially defines like if 2 different nodes are there, like how are they connected in the network, how far are they, or how close are they, like it's defined in the topology.conf. I never looked at SLURM database configuration, but that's more catered to like where the database lives and things like that. Like usually as an end user, we have access to slurm.conf, grest.conf, and topology.conf, but not slurm-dbt. That's only on that should be at least only be on the management daemons that actually run database daemons. Management nodes that run database daemons. Coming to partitions, like I said, these are computational nodes divided into logical partition units, and jobs are queued to these partitions. Like as they come in, jobs are queued to this partition, and a node can be part of more partitions. Well, let's say if a job comes in and it can be submitted to 2 partitions. Like typically we have partitions based on time limits. So we have more nodes for 3-hour jobs compared to less than 3-hour jobs compared to 7-day jobs. There is an overlapping partition. Like the 7-day job partitions are a subset of what we have for 3 hours. So because if I submit a job for 2 hours, they can essentially run in both of these partitions, and they're given a particular priority value based on which partition to go on to. A priority number. In each partitions, like we can define the size of the job that can run. I will quickly go over how these configurations are defined on Gram cluster, since I see almost everyone in today's lecture is coming from Sharpnet. So like I'll go and look at the Gram clusters configuration and look at that. And we can also define access controls in terms of like, if we have a contributor node, we can say who can access those nodes by QoSs using access controls. There is also preemption rule. I don't think, at least on FrontNet cluster, we don't use preemption rules. But what this means is, if there is a contributor node or a high QoS job, high QoS accounts, like preemption, we can make use of preemption to end some jobs or pause some jobs when a high priority job comes in. This is generally not used, but it's available in SLURM configurations. Let me quickly look at the hcv.conf file. I just copied it to my Scratch directory. So if you type in hcv SLURM, that's where all the configuration files are typically in. Some of these files are readable. For example, we can look at the SLURM configuration in slurm.conf. If I do that, like if I did in my own Scratch directory where I copied it to, if I see this essentially defines the configuration. So this defines all the partitions that we have. Probably I'll So there is one partition called CPU base interact. If we look at this partition, like it defines the maximum time limits that the job can run. If I submit to this partition, I can run for a maximum of 3 hours. The minimum amount of nodes that we need to request, like there are certain limits that we can impose on minimum number of nodes that a job needs to request, as well as the maximum number of nodes that a job needs to request to run on this partition. And then we have allow groups. We can specify which groups can run on the cluster. Like typically for the regular default nodes, everyone can run. Like same thing with the contributor nodes as well. There is a factor called priority job factor. This is for preemption, so I'll just not go through that. And we are, as opposed to like allow groups, we can also define deny groups. If we don't want a particular job group to run on these particular nodes, that can be defined as well. And the preemption is off. Oversubscription is something for, let's say, again, this is almost never used on HPC clusters, I think, but I'm not too sure. But if you have 100 CPUs or 100 gigs of memory, like oversubscription means that like and it goes under the assumption that all these resources are not used always. So we have a margin for overbooking essentially typically when an airline does it, like it's a similar concept, but typically it's set to no. And the grace period after the job completion, are there any grace time that we give to the users once the job completes? Like they exceed the time limit, that to clean up their jobs essentially. And allow POS, everyone is allowed here. Same thing with allow accounts. All the groups, all the accounts are allowed to run on this. And finally, this is where the nodes are defined into logical units. These are the list of nodes that are part of these partitions. If we can see some other node, like if you take this particular partition and this particular partition, you can see that some of the nodes will be similar, but usually B2, which is higher time limit, I think it's 24 hours, sorry, 12 hours, has a subset of nodes that we have for 3-hour runtime. So we have one large partition which contains most of the nodes, then that can run jobs within 3 hours. Then we have slightly lower partition which contains fewer number of nodes than B1. But same thing with B3, we have few more nodes, B4 and B5. I'm not sure if we have B6 on Gram, but yeah, we have B6 that can essentially run up to 672 hours. I think that's 28 days. That's essentially how the partitions are defined. A few more things about Gress billing weights. These are essentially when a job runs on this, how much are we charging them to run on it? Like this becomes important for job priorities. Job priority for a user, a line share is based on how much usage they had in the recent past, and Gress billing weights assigns is used to account to calculate how these usage is counted. In this case, CPU is counted as 1 unit, saying that if I use 1 core, I'm going to be charged 1. Memory is charged half of that, like if I use 1 gigabit of memory, I'll be charged 0.25. And how the value is defined is itself a matter of how it's defined in the SLURM plugin. This can be a sum, a simple sum, or most likely this is a maximum of either these two. Like if I use 4 gigabytes of memory, it's equivalent to using 1 CPU core. Even if I use 8 GPU of memory, even if I use 1 core, that's charged as 2 cores. That's why when we do rack applications, we have a concept of core years and core equivalent years. That's where this is coming from, like the billing of these nodes. The reason for that is on most nodes, leaving out the larger nodes, typically we have 3.8 to 4 gigabytes of memory per each core on each node. That's where the reasoning comes. Let me look at another where there is Gress. Probably this is easier over here because we have fewer amount of nodes. Similarly, if you want to define GPUs, we can assign the weights for GPUs as well. So 1 GPU in our cluster is counted as 10 because we have very few GPUs on our system. That's how the partitions are defined in the slurm.conf. Like coming to the partitions that we have on the Alliance cluster, this is a quick summary of how partitions look like. Under the root partition, so this is where the job submit.lua comes in. You can find that in Etsy SLURM as well. So this particular Lua file is called whenever a job is submitted. So, and it actually, what it does is these are all the partitions that we have on the system. Like we have, this is for Narwhal when I made this figure, like there are at least 39 partitions. You will see a typical partition name as CPU base by node or by core, based on whether a user is asking for whole node or whether is asking for fewer just cores within a node. And then B1, B2, B5, these define the time limits. It ranges from 3 to 14 days. And also we have, because we have base nodes which are 4 gigabytes per core, and we have some larger nodes which range up to 16 gigabytes per core. When a job comes in, what job submit.lua does is, it's a bunch of if statements. It reads through the resource request, the things that we defined in the SPatch directives, or if you are using not SLR session, like SPatch directives, or you can submit it through SLURM as well. It takes that and it redirects the job to a particular job submission. Let's say if I'm submitting a job that needs more than 12 gigs of memory, and I'm asking for one node with 10 cores. So I'm asking not for the whole node, but a partial number of nodes for 10 hours of time. So what it does is, it takes my submission script, it passes through it, and it redirects the job to this particular partition. Like it goes through CPU, large, by core, and B2 because it's within 10 hours limit. If in general, if you don't have this job submit.lua, this can typically run both on B1 and B2. And if the request is within, like it might even run on base nodes, but it might use a lot of resources. So in that case, what happens is there is a queue that's been set up for all the pending jobs. In that, like from what I read, like there are 1 or 2 instances of these jobs in the queue, and based on the priority level and which partitions become available first, like that job is going to run first, and the rest of it is ignored essentially. The next set of things is the SLURM needs to know where the jobs need to run. Like partitions are the way to define our job queues. And second thing the SLURM needs to know is what are the resources that are available. This is defined in slurm.conf as well. Again, if you do slurm.conf grep node name, the script will look something like this, essentially defining the node names. Like each node has a host name. This is the list of, you can either name, you can either define the resources that are available for each node individually, or you can define it through a list if you have similar nodes. In this case, all these nodes have a similar compute resources. So it's defining like all the list of nodes that are there, then number of sockets this has. So this becomes important when we submit a job. If we want to bind a job to a particular socket or particular core, SLURM can use this information to assign it. Like, let's say, if I want to, if in my SPatch directives, I'm defining like a job has to run only one socket, like SLURM can take this information and try to only run it on that particular socket. For that, it needs this information. And again, number of threads per core, which essentially means that hyperthreading is not available, and the real memory, number of memory that's available in megabits. In this case, I have, it's a large node, 1 terabyte of 2 terabytes of memory, and the weight of 3 is assigned to it. Like essentially, weight defines how fast or how slow a job, like the priority in which jobs should be scheduled on that. Like, let's say if these 2 nodes become available, I think it'll run on the higher weight node compared to a lower weight node, because it's 512 gigabytes compared to 2 terabytes over here. And There are some features like in terms of mostly CPU architecture is defined here. This is for Narwhal, so it's defining as room architecture for AMD processors and how much temporary directory is available. How much temporary directory is available for this slurm.conf file. Same thing over here. If you are looking at the GPUs, it defines it has eight A100 GPUs, 4 of them, and this is the temporary temp disk. And lower the weight, like it gets started first. Because this is a GPU, that's why it has a 4. And features are defined as Milan, that's the computer architecture, and essentially we can use this in our SPAS directives to ask for a particular node. Let's say if I say features equals Rome, so none of my jobs, although they can run on this, will not be going there. It will go only to the partitions that has that feature on. The next configuration file is the topology. This defines how a network is set up. We don't need to be exhaustive of how typically we have a Dragonfly network system or something like that. The whole thing might not be defined, but the simplest network on how the nodes are linked with each other should be defined in here. In this case, we had Narwhal, or in this case, it's defined as topology tree. And what it essentially contains is we have a rack of servers or a rack of compute nodes connected to a particular switch. So all these compute nodes are essentially connected to switch 0, 1. And I have one more rack, which are connected to switch 0, 2. And these both switches are connected in the tree structure to switch 0, 0. So how this is important is in SBAS directives, there is a flag called switch. I can specify how many hops my job can run on, how many switches it can hop on to communicate. Preferably, we want it to run on one switch, because if I have MPI communications going around, it's better to schedule it on a single rack compared to different racks. And this topology .conf is used by SLURM to schedule it all. It tries to do it. It's not that it guarantees it. It tries to keep everything in a particular rack, or minimum number of switch hops that can be possible. And users can define it as well. You can go through multiple switches, but you can define that only my job can only spread on so many switches. And there is also some config directives to specify in your SPAS directives to how long to wait. Say it might, if a job is waiting for too long, you can specify that I only want to wait for a certain period, 1 hour or 2 hours, if it doesn't schedule, or 2 days. If it doesn't schedule it by that time, there is no real advantage for me to scheduling everything on one rack. I can just go on multiple racks at that instance. There are ways of doing it through SBAS directives, but the information of how SLURMs read it is defined in the SLURM topology.conf. This could be an example of how the switches are set up. This is a basic diagram essentially showing have my compute nodes in a single rack, and those are connected to switch 1, switch 2, switch so on so forth, and switch 10 is connected to this. So SLURM tries to schedule it on one of the racks if possible. If it's not, it minimizes the number of hops that are available, but it doesn't guarantee. That brings us to the end of part section 4. If anyone has any questions, you can unmute yourself or ask in the chat. I will give 1 or 2 minutes before I move on to the next section. Okay, moving on. I will right now discuss about this job scheduling on SLURM, how it does the job scheduling. This includes the algorithms that are available to schedule the jobs. And also the scheduling is done based on job priorities. I will give a quick demo of how we can retrieve this information, and also a major factor in calculating the job priority is fair share value. And we will discuss about like how that fair share value is defined. There are essentially four different algorithms that schedules the job onto the job queues. First is a fixed scheduler and a comprehensive scheduler. This is based on simply the job priority value. Both these scheduling is done based on job schedule value, job priority value. The major difference between the fixed scheduler and the comprehensive scheduler is it looks at the first thing is it only looks at finite number of jobs, whereas comprehensive scheduler looks at the complete queue depth, like whatever jobs are queued in the system, like it looks into it. On I think for quick scheduler, the number of jobs it looks into to schedule is 100 by default, but on our cluster on Gram, I think it's 3000 if I'm not wrong. The second important difference is it's event driven. The quick scheduler is event driven. Let's say if a user submits a job, then the quick scheduler kicks in. That's why the amount of jobs that are considered for scheduling are limited in the quick scheduler. But in terms of a comprehensive scheduler, like it runs at defined intervals. I think the default value is 5 minutes. I think for the comprehensive scheduler on Alliance cluster, this is put to a very large value because this quick scheduler itself considers a lot of jobs, around 3000 or in that order, like to schedule those jobs. Both quick scheduler and comprehensive scheduler are completely based on priority. So if we just go by the quick both these scheduling schedules, like what essentially happens is essentially there is a big job queue as the jobs are submitted, and a queue list is created based on the pending jobs. Like it only considers the pending jobs that are there in the whole job queue, and then like each job is assigned a priority value based on their recent usage, their QoS, and how many shares they have on the system, and how long the job has been waiting in the queue. These are some of the factors that define it. And once the priority list is sorted, if we are going through quick scheduling, the next job at the top of the priority queue is scheduled as the compute resource becomes available, and it passes through the priority list one at a time, scheduling each of the job to the compute resources as they become available. But one particular drawback for this is if we are doing priority-based schedule, there can be a lot of wastage of computational resources. That's where backfilling comes in. This plugin is enabled by default. Like if you go to the slurm.conf configuration file and look at sched backfill, you can see that either it's backfill or built-in. Built-in essentially means that it's priority based. It's completely based on priority. Backfill means that backfill scheduling is enabled. So what backfill schedule essentially does is every once in a while, it looks for the lower priority jobs in the queue. We can define how long it needs to look into the job queue for the backfilling. And if a lower priority job can fit in the job schedule without affecting any of the jobs that are there in the higher priority. Let's say if a job has a rank 10, let's say if 10 can run now, without affecting any jobs from predicted start times. We can't actually predict it because job times always changes and there are always new jobs coming in. But predicted start time by the scheduler, it can fill in this job and start running. To give you a visual example of this, let's say I submitted 5 jobs and this is the shape and size of those jobs. Like there is one job which is only using one core, but like it uses a huge amount of time, like that's 1, 2, 3. And a big job comes in, it essentially uses up all the compute nodes, and based on the priority value, it's ranked to run now. And let's say if there is a job 5 that comes in and it can't essentially fit in any of these, so it runs after job 5. Then SLURM looks through backfilling, like it tries to look for jobs that can run in this particular area, like essentially in this particular limits, so resource limits. So if a job 6 comes in with this size and shape, essentially it can essentially run right now because those resources are getting wasted. So backfill scheduling algorithm kicks in. This runs at regular intervals, and that essentially schedules the jobs on essentially that increases the utility of the system. Again, these are defined in slurm.conf. Like most of the configuration most of the configuration for slurm is defined in slurm.conf, or you can change these configurations to scontrol command. So either you can have so for the quick scheduler and the comprehensive scheduler algorithm, it's based on priority values. So how we calculate these priority values is defined in the slurm.conf as well. So you can say priority, this is defined as priority type, priority basic, which essentially means that the first job that comes in is the first job that goes out, like provided there is no backfilling. Like let's ignore backfilling for now. But in multi-factor authentication, this is what we typically have on our clusters. It calculates the job priority value based on different factors. These include job age, the amount of time that is job has stayed in the queue, fair share, which actually is a major factor in scheduling the jobs. Then you have job size, which is it a smaller job or bigger job? Again, we have configurations to enable or disable this, change this behavior. And then we have partitions, like each partition has a partition tier. And based on that, partition factor is calculated. And that has some weightage as well. Again, if a particular user group has a QoS that can run on a particular partition, some weightage is given to that. And also the resource request, which is essentially the amount of resources that they are asking, they are factored in calculating the job priority factor. Job fair share factor is one of the most important factor, and also the rest of all these factors range from 0 to 1. The age. Okay, go to the next slide. Factors for calculating job priority are floating point values ranging from 0 to 1. And in calculating job priority number, it's essentially a weighted sum. Because it's only from 0 to 1, to capture the minor intricacies, it's better to have priority values which are large integer values. So therefore, we don't lose information in rounding of errors. So that's the major caveat of that, like just to have a larger value so that information is not lost in rounding of errors. Higher the priority number, like sooner the jobs will schedule, ignoring backfill scheduling compared to the other job in the screen. If you look at the job priority numbers, like this is what it looks like. QoS for most users, unless they're a contributed account, QoS is not defined. So if we look at the weight functions, you can see that fair share weight is roughly 5 million compared to other factors that are in there. So it takes a huge chunk based on fair share. And fair share value is actually calculated based on your current usage and the amount of shares that we have on the system. So when we do a rack, like if it's a default account, they have a default number of shares. But if the users, if a group has submitted a rack application, they typically have more amount of shares. And this is where it factors in. Like, so we calculate the fair share value based on their utilization in the at present, as well as the amount of shares they have on that particular system. That's why rack applications and number of shares that they have on the system becomes important. We don't necessarily have a dedicated compute resources for everyone, but the actual goal is to have a particular usage for a particular group based on the shares that are allocated to them, provided everyone uses the system more uniformly. So like I said, like fair share factor ranges from 0 to 1, and I will quickly go over how those values are created. But before I get there, if we want to retrieve the fair share values of the current running jobs, I will do this on frontnet because there will be fewer jobs. If I type SPRIO, which essentially gives me the priority number for that particular job. This function is handy if someone says that why is my job not running yet? Like this can define this can say that their fair share values, and based on that we can say your fair share value is not right, not there yet or something like that. And also there is a function called sshare, which essentially defines level FS. I'll come to that command in a little bit. So that essentially says what are the normal shares that are available for this particular user, raw shares. And there is one quantity called level FS. What this value is it defines your usage compared to your shares. If the value is 1, it essentially means that the fair shares usage is almost equivalent to your number of shares. If it's less than 1, you have the user has or the group has overused their the compute resources. It's greater than 1. It's underutilized. Coming to the fair share value calculation. Again, these values are again defined on slurm.conf. Like if you see cat slurm.conf and grep for priority, those are the values that are defined. There are particular values that are defined here. There are weights, and also there is priority decay half-life. So what this factor essentially says is we are only interested in the usage in the recent past. Like let's say if a user has run something a month ago, that should have less influence than something that the user is using right now in the past 7 days. That's what half-life means. It means that if I use 10 cores 1 week ago, that will be accounted as 5 cores, roughly 5 cores. When I'm calculating the usage in the current time period. That's what half-life of 7 days means. And again, we are using multi-factor authentication. These are some of the flags that are defined to set the calculation period. How frequently is this parity calculated? It's every 5 minutes. Just an explanation of all the factors that I defined in the previous slide is given here, just for reference. If I come to the fair share discussion, the amounts of shares that are allocated to the user is again done in a hierarchical way. Essentially, we have, essentially we have a root like which has 100% of shares that are in the system, and then we have several accounts defined on it. This is typically how it's set up on the Alliance clusters as well. On these accounts, like shares are allocated to these accounts. If it's a def account, it has a default number of shares. If it's a con account, if it's a RRG account, like it has a different number of shares based on the rack that is being allocated for that particular user group. Under the account, like each group can have, according to like in terms of SLURM, like they can have non-equal amount of different amount of shares within that particular group. They don't necessarily need to add up to the amount of shares. Let's say if I have 1 here, essentially that means that I have 1/3 of the shares of what this account is. Just for visibility, like I just made it so that everything, if you sum it up, it goes to 100. So this user has 20% of shares. This user has 20% of shares, and this user has 25, and so on and so forth, based on how I allocated the shares to each of these. In this case, you can see that we have 25 and 15. That accounts for 40% of total. Like the way it's calculated is, it's a geometric ratio of all the parent directories in this case. Like for the current user, the amount of shares that it has compared to all its group members, for that account, like the amount of share that has to all of its group members. So it essentially becomes, for this particular user, it's 15 divided by 40 into 40 divided by 100, because 40 plus 60. So that's essentially how it's divided into. And we can, if you are interested in getting like how many shares are allocated to each of these systems and how it's defined, like there is a command called share. If you type that, like we have a root account, and under that we have CC debug, which is essentially for analysts, like if you want to quickly get some priority. And then we have def, each of the def accounts, and then we have RRG accounts. So that way, like the priority values are set. Like it's in our case, it's pretty much flat, where you have a root. Under that, we have PI's account, or like CC debug, and so on and so forth, or def accounts. Under that, all the users comes in, all the user which are part of that group comes in. Like in this case, it's showing me who are under this CCDB, which I have access to, like Rakesh. Coming to normal usage, the usage is normalized when we are calculating the usage, because we need a factor that ranges from 0 to 1 to calculate our fair share factor. The usage is also normalized. The way it's done is, if we forget about the half-life for a bit, the way it's done is the usage of this particular user in a particular time frame divided by the total usage across the cluster. That gives me the normalized usage for that particular user. If we are taking half-life into account, the way it's calculated is, in each of these periods, like each of the whole usage is segmented into different periods based on how it's defined in slurm.conf. And in each of these periods, like the usage is calculated. This is defined by this, the current period. And then if I have usage in the previous period, it's multiplied by a decay factor. This decay factor depends on the interval and my half-life. It's calculated based on that size, like what's the length of the current period, and also the fair share factor. Like that essentially gives a value of decay factor somewhere ranging from 0 to 1. So if the calculated period is, let's say, 7 days, the decay factor will be 0.5. So the usage is halved every section. I believe the actual calculation is done based on, like, UH is calculated for a previous period, and that is multiplied by the decay factor, and the current period is calculated in the current in the updated scenario. Algorithmically, that's what I think happens. Same thing for RH. RH defines the total usage on the system, similar to UH. The total usage in the current period, last period, and the previous periods are calculated. So as we go further out, the value of the decay factor is less than 1. So as we multiply any factor by n times, like the value goes down. So as we go further, the amount of usage that is considered by calculating the current usage or adjusted usage is lesser, is more influenced by the current period than any of the periods before. And then again, its total usage is normalized using UH by UR, which is defined here. And that's pretty much how the usage is calculated for fair share factor. And initially, I shown how the normalized share is calculated, and the fair share factor is nothing but the ratio between the usage factor, effective usage factor, and the current use and the total shares. And there is this value can essentially go from 0 to infinity, because technically, mathematically speaking, this can go from 0 to infinity because my shares are fixed, but my usage can go, mathematically it can be infinite, so it can go to infinity. So we need to normalize to 0 or to 1. So the way the fair share factor is calculated is 2 to the power minus QE by QS. That's essentially how, and this ranges from 0 to 1. If you calculate it, if it's infinite, it's 0. If it's 1, if it's 1, that's exactly your usage matches the shares. That's 0.5. So fair share factor of 0.5 means that the user has been using exactly the amount of shares that are allocated to that. And then if we just consider this and calculate it, my usage is not affected by the usage by the group. To account for that, the usage factor is slightly adjusted. In this case, UACH is the current user that is using, which is calculated using this formula. And there is another factor that is included in this, which accounts for the usage of the parent or the group, minus the usage of the child itself to avoid double counting. And from that, the usage factor of this particular user is calculated. So my usage depends mostly on my current usage and also the usage of the group. If I have n particular members with equal shares, that's how we typically set up. This is how the factor will look like. It's a weighted sum of my current usage and the parent usage. One drawback of this implementation is, let's say there are 2 users with different job sizes. Like there is one user who has submitted a large job and waiting in the queue, and because it takes and there is one user that is submitting small jobs and using backfilling to essentially start the jobs. And what essentially happens is the priority of the user hasn't run any particular job. The large job user hasn't particularly ran any job. Because of the usage of his group members, his priority continuously goes down, and then it becomes harder to implement it. So if you have 2 particular group members who are having different size jobs, like that can pose problems sometimes. And to summarize job level fair share factor, you can use this command to essentially print out the fair share factor like I've shown in the command line. So anything less than 1 means you are overserved. I actually made a mistake there. And under 1 means that you are overserved your amount of shares. And exactly 1 means that's the factor is 0.5. The level FS exactly 1 means, which is U by US. It means that you're exactly using the number of shares that are there. Similarly, in terms of fair share factor. If 0.5 means exact usage, less than 0.5 means underserved, for greater than 0.5 means overserved. With that, I will conclude my presentation. Thank you everyone for attending.